Hello everyone, welcome back again to the course Comprehensive Slope Stability Analysis using PLAXIS 2D. We are in the Seismic module, lesson 43. The Seismic, we have this tutorial for this lecture. Seismic response analysis of a hillside slope using real earthquake records in PLAXIS 2D. So we have this hillside slope, as you can see in this figure, and we are going to perform a seismic analysis or dynamic analysis using real earthquake records. As you can see in this figure, we have acceleration and time history. So we will apply this real earthquake data to the bottom of this hillside slope, and we will see the response of this slope under the effect of this real earthquake data. So in this lecture we will also learn about seismic boundary condition. When we perform a seismic analysis using real earthquake records, we need to define a special seismic boundary condition, and also we will learn how to import a seismic data in PLAXIS. And also in seismic analysis, it is important to define the damping ratio for the soil. And also we have a drift correction. It's an important in PLAXIS 2D. We will talk about this also. And also we have another important step while defining or applying the seismic analysis in PLAXIS 2D, which is called time stepping. So we will talk about this in detail in this tutorial. So this geometry I have already drawn this geometry in AutoCAD using a two-poly curve. So we will export. We should export this geometry to AutoCAD DXF file, and after that we can easily import to PLAXIS 2D. Also, we have a Rayleigh damping, as I mentioned before. It is important to define the damping ratio for the soil to model energy dissipation, and also the damping value should be a small value to model energy dissipation without over damping high frequency waves. And this damping ratio helps to simulate a soil behavior under seismic loads. So in most cases 5% of damping ratio is acceptable. But also we have these typical damping ratios for different types of soil. For example, for clay soils we can use 2 to 5%, and also sandy soil 1 to 3%, and also gravelly soil we have 0.5 to 2%. Because I have shortly explained here according to Bentley's sources. So drift correction is important because when PLAXIS calculates displacement by integrating acceleration twice, as we know that when we integrate acceleration twice it gives us a displacement. So it might be incorrectly returned to 0 if I don't check the drift correction. That's why it is important to check the drift correction to ensure that displacement is 0 once the earthquake has stopped. So we can see this is a deformed shape at the end of the earthquake, and this deformed shape is scaled up to 100 times greater than the true scale, and the maximum deformation value is about 1.6 centimeters at the end of the earthquake. So you can see we have two phases, but if I click on here, switch between phases, you can see we have more phases, which is 200 phases for the seismic analysis. And for example, if I click on this one, seismic analysis at 1 second, we can see the deformation is different. The maximum value is about 9 millimeters. And for example, if I click on a deformation at 10 seconds, we can see the maximum deformation value is about 5 centimeters. And at the end of the earthquake, we can see the maximum deformation is 1.6 centimeters. Also, we can draw a curve between the deformation and dynamic time. We can click on Curve Manager and click on New. And in the X axis, we select dynamic time, and in Y axis, we select a point. As I mentioned before, we select a point at the crest of the slope, and also we selected a point at some location here and here. For example, right now I want to check the deformation at crest of the slope versus dynamic time. So this is the highest point, and we expand deformation and total displacement and click OK. So you can see how the deformation changes versus dynamic time, and increases to maximum at 6 at the second of 6, which is about 7 centimeters, as we can see. And after that, it decreases to a minimum value, which is about 1.6, 1.7. So in here we can see how lateral stress is increased with the time, and after that it stays constant. So this was for this lecture. I hope it was clear and useful. Thank you for watching. See you in the next tutorial.